Good morning, physics. It is Wednesday, May 13th, and today we're going to be talking about using information from seismograms. And yesterday, one of the things we talked about is how plate boundaries and earthquakes sort of are formed and the different types of waves that can be sent out due to tectonic activity. So what's going to be happening today is we're going to be talking about how we can use those information from the waves to predict earthquakes and sort of where they are. Something which we're going to do tomorrow, which I'll have some sort of digital workspace for y'all to use for finding an epicenter. And we're going to be working on that tomorrow. But today, what we're going to do is just sort of read through Explore, Explain 2 and sort of talk about some of the information here. Now, with earthquakes, there are sort of two real points to go from. You have the epicenter, which is sort of the idea of basically if you were to flatten out the Earth, where the earthquake took place on a map. And then there is the other point, the focus, which is where the earthquake actually originated from. Now, one of the things that sort of happens is as we sort of go through here, there is often a lag time between the two different waves, between your pressure waves, so your primary waves, and your surface waves, your S waves, the secondary ones, which are the ones that cause the most damage. Now, one of the things that sort of happens is based on the time between them, if there's a longer time between the pressure waves and the surface waves, then that usually finds or is sort of evidence that the epicenter is much further away than it would be if there's a very short lag time between the two waves. So that's a sort of interesting thing going on here, and one of the key points is that in order to detect where the epicenter is, you need at least 3 seismographs to measure it. With 2, you can sort of calculate the speed of the waves, but you don't really know where exactly it is. With just sort of 2 circles intersecting, you end up having the possibility of it being from 2 different points, but you are able to measure the speed of the waves based on sort of knowing where it is, like being able to measure from 2 locations and have some time. However, one of the things that you can do is if you have more than 2, if you have 3 or more, you can actually, with 4 you can figure out where the focus is, so where it actually originated from, but with 3 you can figure out the epicenter. And it's kind of interesting and sort of a fun activity we'll do tomorrow is actually measuring how these earthquakes are. You're going to sort of have 3 different seismograph locations and measure out how to do that, which will be fun. And then also for today, we're going to skip this. And then one of the big things is sort of the magnitude of earthquakes. Now, the Richter scale, which is sort of what we use to measure the power of an earthquake, uses what's called the Richter scale, and it's a logarithmic scale, which means that each point is not necessarily a linear increase, but a multiple of the previous point. So, for instance, a 2.0 earthquake and a 1.0 earthquake. So I actually did some math on Desmos using this equation, where MW over here represents your Richter scale value, and this represents the energy released during the earthquake. And so we sort of converted this energy released into this like factor of about 10 scale, which increases exponentially with each new step. So like a 2 is not twice as powerful. So a 3.0 earthquake is not 3 times as powerful as a 1.0. It's about 300 times more powerful than a 1.0, and so on and so forth, where it doesn't just sort of scale linearly, it is multiplying upon itself. So in terms of some quick little math I did using some Desmos, I converted the equations, and sort of depending on the value, where n is sort of your Richter scale, you know what I'll actually do is I'll call this m, And we'll switch all these to M. And what we can do is, if you think about it, you can choose a different value for your Richter scale. I'll share out this graph. And you can see how much more, so like this would be a 4 on the Richter scale, and this would be an 8. And if we do that, it is about 1 million times bigger. If it's a 6, you got 10 million, and so on and so forth, and it sort of keeps increasing. A 1 to a 2 is about 32 times. A 2 to the 4 is about 1,000 times. And then 3 ends up being kind of interesting. But this is sort of the basic idea of what's going on here, and sort of these things, they multiply upon each other and they get stronger and stronger. So it's not just 6.0 is not twice as strong, it's about 32,000 times as strong as a 3.0, which is a very easy thing to end up making a mistake on. And then, because there's sort of like a maximum amount of energy that there's not directly a maximum amount of energy that an earthquake can release, but sort of practically there's an upper limit of how much energy an earthquake could release based on how big the earthquake could possibly be. There's like certain points where it doesn't work practically to sort of go above that, because you're releasing so much energy. It's would be more than like several nuclear bombs going off, and that's just very unlikely to happen within our tectonic movement. So this is the idea for today. So you have some questions to answer, and we're going to be doing this lab on Thursday, this finding an epicenter, and just ignore this other lab, exploring shaking frequency. So it's just answering the questions that are presented on this, and then we'll work on the lab tomorrow. So that is what's going on today. I hope you all find this useful, and I will see you all later.